All right. Welcome, everyone. So today I have the pleasure of hosting Robert Wang. Um, yeah, welcome, Robert. Why? Let's give everyone a couple of minutes to join. While we're waiting, where are you tuning from?
Yeah, right now I'm on the East Coast, visiting Princeton at the moment.
Nice. I'm tuning from Washington, D.C. area, and
Oh.
we have a rainy day. Is it raining in Princeton as well?
It's a little bit cloudy,
Ah,
so.
okay. Here. All right. Yeah. Thanks for joining us. So yeah, today, everyone, we have, as I said, we have the pleasure of hosting Robert Wang. Uh, Robert is currently a senior research scientist at Google Quantum AI and a visiting scientist at MIT. In 2025, he will join Caltech as an assistant professor of theoretical physics, where he also completed his PhD under the mentorship of John Preskill and Tomo Vidic. So Robert's research, like Robert has done research in different areas of quantum information theory and learning theory. Um, and he has won numerous awards. I don't think we can go over all of them, but just to mention a few, he won the Milton and Francis Clauser Doctoral Prize Award. He also won the Google PhD Fellowship, Boeing Quantum Creator Prize, Ben PC True Doctoral Prize, and as I mentioned, many others. Um, yeah, and today Robert is going to tell us about certifying almost all quantum state with few single qubit measurements. Please take it away, Robert.
Yeah, thank you so much for the introduction and for inviting me here. I'm Robert, and today I'll be talking about certifying almost all quantum states with few single qubit measurements. This is a joint work with John Preskill and Mehdi Solomonifer. And if you have any questions, feel free to just ask, and Ali Raza will be able to pass on the questions.
Yes. Please ask your questions in the chat, and I will relay them.
Okay, so let's get started. So we all know that in quantum information sense, a very important thing is to create quantum many-body systems with very intricate entanglement across the entire system. So by creating such a highly entangled quantum system, one can perform very powerful quantum computation that have advantage over classical computers for sensing about the world, sensing various aspects of the world with enhanced sensitivity, or allow us to communicate through a quantum network, etc. And hence, in quantum information sense, all the experimental effort has been really trying to understand how we can best control and generate these quantum systems with intricate entanglement. However, in an actual experimental setup, we will always be subject to all kinds of errors and noise that happen in the lab. So a lot of times when we have some target quantum system that we have in mind that we wanted to create, in reality, we will not be able to do it perfectly in almost all cases. And what we will end up creating is something that might be slightly different if we're good in how we're doing the control, or it might be just completely different if there's some failure in the system setup, or if there's some heating in the quantum system. All kinds of tiny noises would just um, kill off the system and cause it to be very different from the desired one. And hence, in the experimental setting, it's very important to understand if we have actually created the desired quantum state or not. And in order to do so, we need to perform certification. So for those of you that have never heard of the word certification, it's a very simple idea. So what is certification? In certification, we have some desired n-qubit state psi. So this n-qubit state, you can think about it as we know it in our head. This is our target state. This is something we wanted to kind of realize in the real world. We can also think of psi as being like stored on a classical computer. Maybe there's some representation for psi, like a tensor network or a neural network or some other representation that stores this desired state psi. And that's our target state. On the other hand, in the experimental lab, we're going to create some other n-qubit state, rho, which might be close to psi if we did a good job. or it might be kind of far away from psi if there's too much errors or noise in the experimental quantum platform. So the certification task is this very basic task, a very fundamental one. That is, we just wanted to test if the state rho created in the lab, always think of rho as the lab state, is close to the target state psi or not from the measurement data. So we're going to perform some experiments on rho, get some classical measurement, like classical data that entails what the measurement tell us. And then from there, try to figure out if rho is close to psi or not. So here, closeness can be measured in terms of the in terms of the fidelity. That's the almost the most common measure that people consider, or the most stringent measure that people consider, which is psi rho psi. Is it close to 1? If it's exactly equal to 1, then we have prepared it perfectly. But if it's close to 1, then we're also doing a good job. Or if it's far away from 1, so like if it's 0.5 or very close to 0, then we know that we're not doing a good job in creating the state. So that's the certification task. And it's a very old problem in quantum information science. And there have been a lot of different procedures that have been proposed for how to do certification, how to certify that we have actually created the state we wanted to create in the lab. So many techniques and many results have been proposed for doing certification. However, it still remains very challenging to certify um, quantum systems, especially if we work in a many-bodied regime. Like we wanted to certify a quantum system that has, say, hundreds of qubits, and the quantum state is highly entangled. In such regime, it's still experimentally very challenging to do so. And just to showcase some of the challenges that people have been facing or some of the challenges in existing techniques, let me go through a few kind of more widely known approaches for doing certification. So let me start with approach 0. This is not really an approach that people use, but it's a conceptually a very simple approach, but it doesn't really work in practice. So it's based on direct measurement. So recall that, let's say we write out the target state, so psi is the target state. And now let's say the target state is generated by some quantum circuit U applied onto the initial product state, all 0. Then one way to measure the fidelity is that we just, given the lab state, so this quantum state here is the lab state, we implement the inverse of the unitary U. So apply U dagger. And then after applying U dagger, we just measure all the n-qubits. If we see that the n-qubits turns out to be all 0, then we know that this lab state is quite close to psi. However, if we saw that outcome is not all 0, then we know there are some errors that pop up. So this is a very simple approach. However, this approach has a very big issue, which is it assumes that one get access to U dagger. So if we can assume that we can apply the inverse of U perfectly in order to run this approach, then the creation circuit, U, should also be perfect too. Like they're in a way symmetric. It's just running the circuit in reverse. And hence, in the world where we can really implement U dagger perfectly, then roles should be able to be created to be equal to psi perfectly. And hence, in this world, there's no need to do any certification. And hence, no one really runs this approach, so I call it approach 0. It's very simple from a theoretical and a conceptual point of view, but because it requires just like to perform this direct measurement, it requires a resource that's as hard as just generating the state psi itself, and hence this kind of defeats the purpose of doing certification, and hence no one actually uses. So now let me move on to another approach, which is based on randomized Clifford measurement. So instead of implementing the specific circuit that invert the target state back to all 0 state, we just run a random Clifford circuit. So we sample a random Clifford circuit and run it, and then measure in a single qubit basis. And now from this formalism known as classical shadow formalism that we came up with several years ago, one can show that the measurement data allows us to efficiently predict fidelity, which is the quantity of interest, psi rho psi. And by just checking that prediction, whether it's close to 1 or not, we will be able to perform certification. However, it is well known that a random Clifford circuit will be linear depths. So if there's n-qubit, the depths of implementing random Clifford circuit on a geometrically local setting would be a polynomial in n, and hence, or linear in n. And hence, while it only requires depths n random Clifford circuit, the depth is still pretty high. It still remains experimentally challenging. Um, People have actually been using this procedure for system size n. That's not too big, like maybe 20 or at most 30. But when one wants to apply it to like hundreds of qubit, then suddenly a linear depth random Clifford circuit is already too deep, and it becomes experimentally challenging to actually run this procedure. So
Can I ask a question about approach zero?
yes,
So if you make some assumptions about U and U dagger, let's say the noise on them are similar, some symmetry assumption,
right.
you then sort of infer the errors by applying U dagger and
Ah,
make rigorous statements that like
yeah,
because you
I
want to
think
certify, right? Yeah.
Yeah, I think in so one needs to indeed like in that sense one needs to say, for example, try to impose certain constraint on noise. But for
Mhm.
example, if the noise is just over rotation, so like when I implement this gate, I will over rotate. But when I implement the inverse of that gate, I will also over rotate. Then actually in those cases, we will never be able to see the over rotation because like maybe in U it would over rotate forward, but then in U dagger it would over rotate backward and cancel each other. And hence in that regime, we can also just run this procedure and see how many times we get all zero out. Under some stronger assumption on noise, I do think that the number, like how many times we get out zero would have some meaning to it. But then it might only be able to capture maybe some incoherent noise, but not be able to capture like coherent noise and so on. So in that regime, like if one makes stronger assumption, not just assume rho is arbitrary, then I think approach zero could still make sense. And actually, there are procedure that were of that form.
Great. Thank you.
Yeah, thank you for the question. So now let's go back to approach two, based on randomized Pauli measurement. So in this approach, we will remove that deep circuit. We now have our lab state role, and then we just perform some single qubit measurement. For each of the qubit, we're going to measure them in a different basis to get a different outcome. And again, using this classical shadow formalism, which is a general formalism for analyzing randomized measurement, it allows one to also predict fidelity. However, due to the lack of using any entangling gate, it's just single qubit measurement at the very end, one can show that while it only requires single qubit measurement on the lab state row, it does have this challenge, which is it requires exponential number of measurements for most target state psi. And here most means if I just consider the entire block sphere and then I consider one target state, most of them it will require exponential number of measurement. But more precisely, it means that when for most quantum state, they're going to be highly entangled, and hence for psi that's highly entangled, the randomized Pauli measurement will require a huge number of measurements. It still works for a small system, like n is like 10 or something. But then as n becomes 100, this number of measurement becomes too big. However, I should also note that if the target state psi has low entanglement, then in many cases, this approach could also work. Because from the measurement outcome, one could predict some local property, and the local property sometimes tells us about the fidelity if the state is low entangled. There's another related approach called cross-entropy benchmark, but it's even simpler than randomized Pauli measurement. So here we have our quantum state, the lab state. What we do is we just measure the whole system in the z basis. So now it will just collapse it into a bit string. And we just look at the samples of bit string that come out of XCB. And from there, one can utilize this. One can utilize the standard approach in cross-entropy benchmark to estimate the cross-entropy and establish this value called the XCB score. And now by checking XCB score, one can say like, okay, If the XCB score is close to 1, then I say I've do a great job in creating the right state. But if XCB score is close to 0, I say there's a lot of noise. So the advantage of this is it only requires single qubit measurement, the Z-basis measurement on the lab state roll. But the key challenge is that it actually doesn't really rigorously address the certification task. Because here, if we only measure in Z-basis, effectively you're only looking at the diagonal part of the density matrix row. And we're not going to see anything about the off-diagonal parts. And hence, if the off-diagonal parts has a lot of error, in a way, an off-diagonal part is like really the quantum part of the density matrix row. So if there's a lot of errors on the quantum side, the XCB cross-entropy benchmark might still report a perfect XCB score if the diagonal part or the classical distribution part is perfectly correct. And hence, even if there's a perfect XCB score, the true state roll might still be very far away from the target state site. However, in various, again, like in some if one assume that the noise on roll has a certain form, then in some of these restricted regime or kind of more conditional regime, then XCB could be a pretty good estimate. However, from a more rigorous perspective, like maybe there's coherent errors, etc., again, XCB might fail quite badly, which we will show later in the numerical experiments. So just some, yeah.
Robert, one question from the audience. I believe it was about approach 2.
Yes.
And can you give some intuition why one needs exponential in n measurements?
Yeah, that's a good question. So just to kind of say a few more words about randomized Pauli measurement. So by performing each cube, like measuring each qubit in a random x, y, or z basis, each of them completely independently. So this may be x, y, and then this is x, z, and so on. We will be able to efficiently estimate any reduced density matrices. So if we have like a 5-qubit reduced density matrices, like this qubit, this qubit, this qubit, and some other two, then we can efficiently learn them using this approach. However, the tricky thing is that as the reduced density matrices start to grow, like if it's now 6-qubit, 7-qubit, 8-qubit, and so on, the number of shots in order to get the error, to get the estimation error down would grow exponentially in the subsystem size. And hence, in a way, once you really think of these randomized Pauli measurement, at least when one you to go through the standard classical shadow formalism, is very good at capturing local reduced density matrices or local observables. But now if we have this target state, which is highly entangled, like think of the observable that we wanted to predict is psi, ket psi, bra psi. That's a, like when psi is highly entangled, then that observable would be highly non-local. And hence, in order to use the standard randomized Pauli measurement followed by classical shadow post-processing, one would require a huge number of measurement in order to get that error down. So that's some more intuition on the challenge that one faces when one just applies this. Like randomized Pauli measurement is really most useful when the goal is to estimate like Hamiltonians, local observables, sum of local observables, or reduced density matrices, entropy of subsystems, but for small subsystems, etc.
Thank you.
So just to summarize some of the existing challenges. So as of now, all existing certification protocols, they either require a deep quantum circuit before measurement. And in that case, the number of measurement would actually scale pretty good. Like in randomized Clifford measurements, the number of measurements would scale independent of system size. So even if we have 1,000 qubit versus like 1 qubit, the number of measurements to do certification to estimate fidelity is the same. However, if we don't allow applying deep circuit because deep circuit are challenging, then we need to use exponentially many measurements if we wanted to perform certification on highly entangled state. Or if we wanted to limit ourselves to only polynomial number of measurement, then in that case, it only works for some specialized target state, like when psi can be represented by a matrix product state, or when psi is low entangled, and so on. Or finally, if it somehow works for general state, works, yeah, doesn't require a deep circuit and only need a polynomial number of measurement. In many cases, it would now lack a rigorous guarantee that it will work in all cases. It might work in some restricted cases, like when the lab state is subject to white noise. But when the lab state is subject to coherent noise or some other more um, also pretty reasonable noise, then they might fail pretty badly. So this raises the following question, which is, can we rigorously certify highly entangled quantum state by performing few single qubit measurements? So this question is essentially left open from the previous work. Or if you're even more ambitious, one can ask, can we rigorously certify almost all quantum state by performing only few single qubit measurements? And this is the question that we're going to set out to answer in this talk. So the outline of the talk is as follows. First, I'm going to present the theorem that says the answer to this question is actually yes. And then I'm going to talk about the protocol for establishing the theorem, and finally talk about some applications one can use these new protocol for. So let me begin with the theorem statement. So note that the theorem might seem a little bit magical, but hopefully it will be cleared up when I talked about the protocol. So the first theorem states that for almost all n-qubit states psi, we will be able to certify if the state in the lab, if the lab state rho is close to psi or not, using only order n squared single qubit measurements. Recall that previously, if one uses like randomized Pauli measurement, then this would be exponential in n. On the other hand, if we use an XCB, then this theorem also doesn't hold, because if we do XCB, rho might be very far away from psi, even when one gets a perfect XCB score. So this theorem says there's actually a protocol that allows us to circumvent it and work for almost all n-qubit target state psi. So recall that psi is the thing we wanted to create. Rho is the thing we actually create in the physical world. So one lives in our imagination, one lives in the physical world. And furthermore, the certification procedure applies to any rho. So we don't need to make any assumption on what kind of errors is happening in the experimental lab. There could be coherent error, there could be white noise, there could be all kinds of errors. As long as there's too big of an error, then the certification procedure would say, oh, there's too big of an error, and it will be able to catch those errors. And if the rho is actually close to psi, then it would also be able to say, yes, it is close to psi, and we have did a good job. And furthermore, one can another interesting aspect is that even when the target state psi has an extremely high circuit complexity, the number of measurements only grows as order n squared. So even if there's exponential in n circuit complexity, the single qubit measurement is still order n squared. That's another very nice aspect about this theorem. So one might ask, so this theorem essentially answers the question in the positive. It says there is, if one is clever enough, run the right procedure, then one will be able to certify any state rho with just single qubit measurement. One could think about it in a different way. Suppose psi is a highly entangled state in that we wanted to create. Intuitively, it felt like single qubit measurements will only be able to showcase what are the local property, because they're essentially a very localized measurement. We're not doing any entangling gate. And hence, somehow it's telling us that by just looking at each qubit individually, we can somehow already see some of these high complexity entanglement, which is one of the surprising aspects of this theorem. Because for example, if you use randomized Pauli, which is also single qubit measurement, it only allows us to see local things, which also matches intuitively. Like local measurements tell us local things, but the theorem is telling us that local measurements can actually tell us about the underlying highly complex entanglement. However, there is this kind of unsatisfying part about the theorem, which is that this only works for almost all state, but not for all state. And in practice, what we often care about is we have a specific target state psi that we wanted to generate. So even though this theorem is nice, it says for most of these states, we will be able to certify them most of these target state, we will be able to certify them. In practice, we only care about one. Like that state psi might be very useful for sensing or for simulation, etc. So then we will actually want a theorem that can be more specific. Given a state psi, how can I tell if that state psi can be efficiently certified or not? And in order to establish that, we need to define a notion called relaxation time. More precisely, we need to connect the task of performing certification to somehow a kind of an abstract idea of suppose there's a person randomly walking on a Boolean hypercube, how quickly would it spread out to become close to some stationary distribution? So this is a new kind of a connection that we discover in this work. So to be more precise, suppose we have a very specific n-qubit target state psi that we wanted to create in the lab. And now we will also choose some basis. So we're going to fix a basis, B, where B is a bit string. So this could be the standard Z basis, but it could also be some other basis, like maybe some qubit is in the X basis, some qubit is in a Y, and some qubit in the Z basis. Choosing this basis can actually be important and could change this relaxation time. But for now, we're just going to fix the basis. So given psi, we fix a basis. Now when we measure psi in this basis, it would generate a distribution over these bit strings. So we call that the measurement distribution, pi of b. And we can think about pi of b as a distribution over the Boolean hypercube. So we write down this Boolean hypercube where each two different bit strings are connected if they differ by, say, at most 1 bit. So now we have this pi of b, which is a distribution on this Boolean hypercube. We will define a random walk on this n-bit Boolean hypercube. The random walk is very simple. Suppose that we start from some point b. Now what we would do is we will randomly pick one of the neighbor. Say we pick b prime. Then what the walker would do is it will, with probability proportional to pi of b, state in the bit string b. Or with the probability proportional to pi of b prime, jump to the bit string b prime. So that's the random walk. It would start from somewhere, like b, select a random neighbor, and then either stay or jump there. And then we just keep doing this step for some round. And the notion of relaxation time, it's very closely connected to what's also known as mixing time. They are off by a small factor, but they're essentially the same. Essentially, it's the time it takes for this random walker to like after, okay, so initially it would start at some point. So where does it start? It would start at a point that is being sampled from the measurement distribution. But once you think about it as when it starts there, it would be a kind of a point-wise distribution. Probability 1, it's there. And now after one step, there will be the probability will start spreading out. And then one could ask, how many steps does it need to take such that it will be spread out to become kind of close to the measurement distribution? It doesn't have to be exactly equal. It just needs to be like constant close by a small constant. And that minimum time for it to take to relax to the stationary, like starting from point, start to relax to the stationary distribution is known as relaxation time, or it's also closely connected to the mixing time. So we let tau to be the time for it to relax to the stationary distribution pi. Now we have the second theorem, which states that for any n-qubit state psi, that with a chosen basis b, that would induce a relaxation time tau, then we can certify whether the lab state rho is close to psi or not using order tau single qubit measurement. And furthermore, we can restrict ourselves not just to general single qubit measurement, but to independent Pauli basis measurement. That is, we just measure each qubit in a random not fully random Pauli basis, but in some Pauli basis. Then in that case, we can show that we also only need order tau squared single qubit measurements. So this theorem essentially allows us to focus on a specialized state, pick a basis. Sometimes the basis would actually change the relaxation time. But we can say pick the basis randomly and hope for the best. But yeah, pick a basis, it would induce a relaxation time. And now the relaxation time actually dictates how many measurements do we need in order to perform certification. And how one can get theorem 1 is essentially showing that for actually almost all state, for most of the states, the relaxation time is bounded by order n squared. It's only quadratic in system size, and hence the number of measurements would be quadratic in system size. So that's the relation between theorem 1 and theorem 2. Theorem 2 is more general and allows us to specialize to a specific state. So now after talking about the theorem, we can say, okay, so what is the protocol that allows us to certify some of these highly entangled state or certify almost all state using such a small number of measurements, where prior results would require an exponential number of measurements to just check if the entanglement is the one we want or the state is the one we want. The protocol is actually very easy. We just repeat the following for a few times. Where the few, like how many times do we need, it depends on relaxation time, tau. And the protocol is like this. We have our quantum state, and we're just going to do some single qubit measurement. And how do we do it? First, we will randomly pick one of the qubit, say qubit x, this guy. And then for all except that qubit, we will measure in a z basis. So let's say we already fixed some basis. So now the z basis according to the fixed basis. So we just measure everything in the z basis. And then for that single qubit that we chosen, the random qubit that we chosen, we will measure that random qubit in a XYZ basis. So randomly pick a qubit, everything else measure in a fixed basis, and for that chosen qubit, measure in a random Pauli basis. And that's it for the entire procedure. So we just repeat that for some number of times, which for most states, it will be order n squared number of times. And for a specific state with mixing time or relaxation time tau, repeat that for order tau squared times. And that finishes the experimental part. So it's a very simple experiment that we do in a lab. And now the question is, how do we post-process these data? How can these data from these simple looking experiments tell us whether the lab state that we are measuring on, getting these data from, is close to the target state psi or not? So the post-processing looks like this. And we're going to also look at one shot each time. So one shot means we will pick one random qubit, measure everything in z basis, which generates a -1 bit. And then for that one qubit, we will collapse it into a random Pauli basis. So first, the measurement outcome on the z basis measurement, or these pink ones, they will specify 2 bit string that differ exactly by 1 bit. And the reason is because the measurement outcome give rise to n-1 bits. And then there's 1 bit that is not yet determined, which corresponds to the blue qubit here. So if the blue qubit turns out to be 0, that's B0. If blue qubit turns out to be 1, that's B1. So the measurement on the z basis actually tells us an edge. It specifies a random edge on the Boolean hypercube. So one can think about it as every time when we perform this measurement, we will be able to see one of the random edge on the Boolean hypercube, B0 and B1. And now what do? We look at our ideal state. So for the ideal state, when we perform this measurement on the n-1 qubits, after the measurement, the qubit x will be collapsed into a specific 1 qubit state, psi b0 b1, which is proportional to this state shown here. b0 psi 0 plus b1 psi 1. And one could think about that as being kind of like corresponding the probability amplitude for this point as well as for this point. And it's like a superposition of this. So in a way, the post-measurement state on this qubit essentially tells us information about how does the probability amplitude between the 2 vertices on this randomly chosen edge kind of look like. What is their relative probability amplitude? So now what we would do is we will use this randomized Pauli measurement on this qubit x plus the classical shadow formalism. So what can classical shadow do? Classical shadow apply onto, or which is a method for processing these randomized Pauli measurement, can give us a one-shot unbiased estimator for the post-measurement state on this qubit. The post-measurement state for the lab state, for the thing in the lab, the real one, not the ideal one. And because it will give us an unbiased estimator, we can then use that unbiased estimator for the single qubit state to measure the fidelity with the ideal one qubit state. So we can essentially predict the fidelity. We cannot predict it super accurately, but we will get an, again, unbiased estimator. So what is unbiased estimator? It just means it will fluctuate, but the average of the fluctuation, or the average of that random number, will be the true fidelity on that one qubit state. So we call that omega. And then what we do is we just average over the entirety of experiments. Note that up until so far, I'm just talking about one-shot experiments. So the procedure is pick a random qubit, measure everything else, and measure that single qubit in XYZ. Given this one shot, how do we analyze it? We essentially just look at what is the ideal post-measurement one qubit state on qubit X, and then use the classical shadow formalism on qubit X to predict an unbiased estimator for the fidelity with it on this qubit. And then we just average over all of these shots. And after averaging over, we will get an estimator, a pretty good estimator, for the true expectation value of this one qubit fidelity omega. And we call that one qubit fidelity, or this kind of post-measurement one qubit fidelity, the shadow overlap. So why do we care about this quantity? Like, what is the significance of this quantity? The key feature that we prove in the work is that this shadow overlap E omega actually accurately tracks the true fidelity psi rho psi. How does it track it? Essentially, we can prove that if the shadow overlap is close to 1, it implies that the fidelity would be close to 1. But there will be a slackness that corresponds to the relaxation time. On the other hand, if the fidelity is close to 1, it also immediately imply, one can show, that the shadow overlap would also be close to 1. And hence, by just looking at if shadow overlap is close to 1, we will be able to check if the fidelity is close to 1. They're not exactly the same. They can move a little bit differently. They can move differently, which I will show later. But if the goal is to do certification, then they match up very nicely. Like if one is close to 1, then the other is close to 1, and vice versa. So now to provide more physical intuition for shadow overlap, let me just write down this explicit formula. So the explicit formula is like this. First, there will be an average over different qubit I, and then there will be a sum over different n-1 bit string corresponding to everything except for qubit I. So think of I as the one we choose. We're going to choose that randomly, and then we are going to sum over all different n-1 bit. And then we're going to estimate this quantity. So this b not equal to I rho b not equal to I, one should think about it as this is the probability that we will get this b not equal to I bit string multiplied by the post-measurement one qubit density matrix. On the other hand, the right-hand side here, this yellow one, that's essentially the same as what is the post-measurement one qubit state for the ideal target state psi. And we just take the inner product between them. We take the fidelity between them. So this just kind of writes out more succinctly this whole post-processing procedure that I was talking about earlier. Now we can plug in some simple state. Let's say the lab state is all plus, but actually the target state is all minus. In this case, the fidelity is 0. We can also plug this into the formula above, and we will find that the shadow overlap is also all 0. However, things start to deviate. If we say the lab state, we're actually doing quite a good job. It's only the final qubit is flipped. It's a plus instead of minus. In this case, the fidelity, which is a very stringent definition, will still give us 0. On the other hand, what shadow overlap would give us, if we plug into the one above, is that it would actually give us n-1 over n. And more precisely, if there's like k qubit that are being flipped, then the shadow overlap would be n minus k over n, whereas the fidelity would always be 0. So shadow overlap provides a has this Hamming distance flavor for some of these states. So it could deviate. It doesn't always track fidelity exactly. It could deviate from fidelity, but it deviates in a very natural sense. It deviates from a more like Hamming distance flavored. And that's because it's kind of looking at each qubit individually. Um, but yet, shadow overlap, while it only relies on performing single qubit measurement, but it can tells us about this fidelity. So as long as fidelity is close to one, then shadow overlap is close to one. But if fidelity is zero, then shadow overlap will be far from one, but it might not be that far. Like it would depends on like it has this more like Hamming distance flavor, and that's corresponding to like this slackness here. The stackness here essentially corresponds to shadow overlap having more like a Hamming distance flavor compared to fidelity.
Uh, Robert, before we move to applications, there are some questions from the audience.
Yeah.
So let me start. All right. So one question is, do we need tau squared copies of this state for the protocol? Because it's the relation between tau and n that needs a clarification. And
I mean, is it mostly tau? Tau, or is the question about copies, or is the question about kind of yeah?
copies of this state, yes.
Yes. So in order to run this protocol, I mean, actually, in order to run any learning protocol for in the quantum system setting, because whenever you measure a quantum state, it will collapse the whole system. So now you no longer have the same state anymore. But what one would usually do is one would use the same physical process to prepare another sample of this state. So note that a density matrix in a way is already has a notion of sample. Like every time we're preparing some pure state, but there's a randomness and there's noise in it, so hence it becomes a density matrix. So one copy of a density matrix should be thought of as like a one sample.
Mhm.
So indeed, this requires each measurement, each of the single qubit measurement requires one sample of the quantum state, which can be realized by just running the entire physical process for generating one state one time. And that's basically a necessity for any protocol or any learning procedure
Mhm.
if one works in the quantum world.
And can one think of this? This is another question from the audience. Can one think of this as a directed diffusion on the space of quantum states? Is that
Oh, yeah. So from in a way, I guess is that more talking about like this relaxation time? I think here it definitely has a lot of flavor on this diffusion. One can think about this random walk as being like I'm on a point and then I'm kind of diffusing on this Boolean hypercube, and the diffusion is kind of determined by the quantum state. So there is a lot of flavor here, but I should say this whole thing, like this whole part, is only in our kind of again, it's in our kind of mathematical world. It's in our imagination in a way. In the experimental protocol, we're not doing any kind of actual diffusion of
Mhm.
of the system. So why is the two related? The relation is like this. It's like so like what the measurement protocol is essentially doing is essentially checking like there's this exponentially big cube, and now I'm just looking at a small number of these edges. Like I'm randomly sample these edges based on the measurement, and I'm just checking, kind of like I'm just checking if the if the edge behaves the right way, because we're just taking this fidelity that essentially help us check if the edge in the lab state behaves the right way as the ideal state on this random edge.
Mhm.
And now the idea is like, suppose that most of these edges are behaving in the right way. And what that means is when we now perform this diffusion on this Boolean hypercube, this random walk, then the random walk would be correct. And then because the random walk will now walk to become the entire state, and then hence, if when we check a few edges, it all look correct, then it means that the whole state actually looks correct. And that's how we get this, this key feature. And this is the only place where the relaxation time pops up and the notion of random walk pop up. It's in this key feature that shadow overlap being high means fidelity is high. So that's kind of the relation. So in the experimental world, we're just checking edges. We're making sure that when the walker is random walking, that the edges that it's going to use is going to be pretty good. I
Right.
think that's the
So we have many more questions, but I'll let you proceed with applications, and then if there's time, I'll ask the rest.
sounds great. So now let's dive into the application after seeing the theorem and the protocol. So one can ask, like, why do we care about certification? I mean, initially I did motivate it, but then actually certification is really a very foundational thing that have many applications if one try to be a little bit more creative in how one uses it. So let me start with the more direct application, which is the starting motivation for doing benchmarking. That is, we wanted to use shadow overlap to check if the state created in the lab has a high fidelity to the state I wanted to generate. And here I'm going to present some numerical experiments comparing to XCB for different state and for different noise model. As a starting point, let us look at a situation where XCB is known to work. So here we have a random target state. So the target state is randomly sampled and is fixed. You just wanted to create some random state, which is highly entangled. Just 4 qubits, very small. And then we assume that in the experimental setup, in the lab state, there will be white noise. So we prepare essentially psi, but subject to some global depolarizing noise. So this is a situation where it's well known that XCB works. Actually, in a way, XCB is designed so that this situation will work. And now we can look at the plot here. As the white noise starts to increase, we do see that the true fidelity would have to go down. And we see that the XCB is performing pretty well because it's known to work. It's designed to work in this case. And it's also performing pretty well and going down. On the other hand, we see that the shadow overlap is also tracking true fidelity very well. That's kind of a sanity check to show that shadow overlap in situation where XCB works would also work. And the same holds for 20-qubit. Now we can say, what if it's not white noise? Like in the experimental setting, white noise is kind of an idealized noise. There could be a lot of other noise, non-unital noise, coherent noise, etc. So here's another situation where instead of having white noise, we have coherent noise. Now in this situation, there's no longer a rigorous guarantee for XCB. In coherent noise, XCB might fail pretty miserably. But in hard random state, it is failing, but it's not failing too bad. So as the true fidelity start to go down, like as coherent noise start to increase, the true fidelity will start to go down, and XCB and also go down. However, we can see that it starts to deviate quite a bit from the true fidelity. Like when the true fidelity is still around 0.8, it might be reporting a number that's 0.7. So here it's actually underestimating the true fidelity. On the other hand, shadow overlap, it tracks the true fidelity much better than XCB because, in a way, shadow overlap, as we have seen from the measurement procedure, even though it almost measures everything in the Z basis, XCB measure everything in Z basis, shadow overlap measures almost everything in the Z basis except for 1 qubit. That 1 qubit, it might measure in a random XYZ, and just that tiny bit of additional change actually help it greatly in seeing coherent noise, in seeing the off-diagonal elements. And that's how we establish the theorem, and this can also be seen from a numerical perspective. For a bigger system, likely due to some concentration of measure type argument, XCB in this case performed quite well. But this is for hard random state. So now we can also look at a more structured state. Let's say we have some product state and we just apply some phase onto it. Now again, we look at the white noise regime. In white noise, it's again, XCB is known to work. But in this case, we saw that XCB has a much bigger fluctuation. So the standard deviation for the XCB estimate is very high. So here we're comparing the same number of shots. XCB requires actually has a much bigger variance. Even though its expectation value is correct, it has a big fluctuation. On the other hand, shadow overlap has a much smaller fluctuation and captures the true fidelity very well. For 20-qubit, similar situation happens. And now we can look at random structure state, but under coherent noise. Now this is really in a regime where XCB are really have no guarantee at all. And when we apply it, when we look at this case, when there's coherent noise in the system, and this is a structure state, and suddenly we see that XCB is going kind of crazy. So as the coherent noise starts to increase, somehow XCB was saying that, oh, the fidelity is actually increasing, and somehow it's increasing beyond 1. And I should say, this is because this is a regime where XCB is yeah, XCB is not a rigorous protocol because it only looks at diagonal. It cannot look at off diagonal. So coherent noise is basically affecting the off diagonal. It would also affect the diagonal part, but it might affect it in an unexpected way. So there might be a lot of noise in the off diagonal part, but on the diagonal part it might be less noisy, or it might be the opposite of noise. And in that case, somehow the XCB is behaving in a very unexpected fashion. The true fidelity is still going down because there's more noise. Shadow overlap is tracking the true fidelity well, but then XCB is just going pretty wild. In 20-qubit, similar situation still happens. It's not as wild. As the true fidelity start to go down, we see that shadow overlap tracking very well, but XCB is overestimating it quite substantially. So as we can see when we have coherent noise instead of white noise, XCB sometimes can underestimate true fidelity. Sometimes it can significantly overestimate true fidelity. And in a way, that's just showcased that XCB, as stated earlier, it doesn't really have rigorous guarantee. So if you have a lab state that have some other type of noise that are not white noise, then the behavior of XCB can be pretty wild. And coherent noise is one of a point where this is like one of the common failure mode for using XCB. So that's the first example for benchmarking. But now we can be a bit more creative in using this certification protocol. We can also use it for doing machine learning based tomography. So suppose that there's a lab state, there's a state in the lab, and now here we're not trying to do benchmarking. We just wanted to learn what is that state in the lab. And we wanted to essentially turn that state in the lab into a classical neural network representation of that state, also known as neural quantum state. I have a lot of very exciting progress in recent years. So a neural network can represent various kinds of quantum state, even those with volume law entanglement. However, one of the key challenge, and how can we use shadow overlap in this regard? Essentially, we can think of it this way. So the lab state is fixed, but then there's a model for the target state psi. So think of the psi as being the thing in our mind. And now we are going to vary the model state, the target or the psi. We're going to vary psi to maximize the shadow overlap, because shadow overlap essentially allows us to check the thing in the real world and the thing in our mind, in our imagination. So here, the thing in our imagination is this neural network representation, and then the thing in the real world is fixed. Now we can vary the thing in our imagination, this neural quantum state, to try to maximize shadow overlap or maximize some other loss function based on shadow overlap. And then because shadow overlap just has this nice property, which says that if the shadow overlap is close to 1, it means that the lab state and the target state is close in a stringent fidelity. And hence it allows us to perform a certification of the ML model. So prior to this work, there have been a lot of results or work that try to utilize neural quantum state to do tomography, to learn a lab state. But one of the key challenges that people have faced is that it's oftentimes very hard to judge if the neural quantum state is hallucinating some property. Like we collect some training data from the experiment and now we use it to train neural network. And now the neural network might hallucinate things. It might thought that there's some pattern in the quantum state, but actually there's not. And then if those kind of things happen, which sometimes it does, sometimes it doesn't, then when it does, the prediction coming out of the neural network can be completely wrong. And hence you might thought that, oh, maybe my state has topological order or has some exotic property, but actually there's not. And hence in those settings, it could be kind of dangerous in applying neural network because it's a heuristic and then it has it can hallucinate and so on. But now if we use shadow overlap to certify the neural network model to check that this is actually close to the experimental setting, and now we can be certain of all the prediction that come out of the neural network. And then we can use that neural network in a very rigorous fashion. Like now, after certification, the prediction from neural network would all be accurate because it has been certified. And then we can make a build scientific statement based on these heuristic and very powerful neural network model. So that's another application. So let me just showcase a little bit more in detail. So let's say we have the standard neural quantum state, which is just a neural network given some bit string, it will spit out the probability amplitude that allows us to represent some wave function psi. We're going to use a variant of it because in a way, in our setup, in order to estimate shadow overlap, we need to always compare between two bit strings that differ by 1 bit. So we're going to define this kind of relative neural quantum state where given two bit string that differ by 1 bit, it will tell us what's the ratio of their probability amplitude. Note that this also represents psi because we can just use this neural network for n times to kind of just multiply this ratio. We fix some bit string as a starting point, and now just multiply these ratio, and it will allows us to get the probability amplitude for any other bit string. Now we're going to train this neural network using using shadow overlap. So we're going to consider some 120 qubit state with extremely high circuit complexity and volume law entanglement. And hence the purity, which as like the subsystem purity, which is a measure for entanglement, will go down exponentially. So in the bulk of it, it will always be exponentially small, and then it will come back up. Now, when I randomly initialize this neural quantum state, it's being initialized into some product state. So the subsystem purity is all one, meaning that there's no entanglement across different cuts. And now what we can do is we can train a loss function using this kind of the same measurement data that was used to estimate shadow overlap. We define a log loss that was based on the same experimental data. And then after that, we can use like a kind of a verification set or a test set, validation set, or a test set to certify whether the neural network is really doing well or not using shadow overlap. So here is just training dynamics. So in the x-axis, we have the number of training steps in the neural network. As it starts to train, originally it's just kind of wobbling around, trying to explore the landscape, and suddenly you find the right structure, and then it quickly goes down. So the log loss decays very quickly and then becomes very good. And we can also look at the behavior, but then we don't really know if it's actually good. Like the log loss just tells us it's 0.35. How do we know if 0.35 is the best? Like it actually fits the actual experimental system, or it's not. But then what we can do is we can look at the shadow overlap. The shadow overlap, we see that originally is 0, but then after it's going down, it's also shoot up, and it shoot up to become 1. And when it's 1, we also know that the fidelity would be 1. Note that here, even though I'm plotting the fidelity, but in the actual experimental setup, it's very hard to estimate fidelity. All we can do is estimate the shadow overlap, because shadow overlap can be estimated using single qubit measurement. So now by looking at shadow overlap, we see that it's very good, which implies that the fidelity would also be pretty good. And together, we can make sure that all the prediction from the trained neural network, in this case, will be accurate. And so now when we use the trained neural network to predict the subsystem purity, we see that it tracks the ground truths very well. But furthermore, we have a certification that come from it, that come from shadow overlap. So now the other example is we can then turn the things around. We still have a target. We now fix the target state, there's psi, but now we allow the lab state to change. We try to optimize the circuit in the lab to maximize the shadow overlap with psi. And that allows us to optimize circuit to prepare our desired state. So here we consider constructing some n-qubit matrix product state in a one-dimensional geometry using Hadamard, CZ, and T gates. We consider a setting where we do know what's like the kind of the optimal sequence for generating that MPS. And let's say we just run the optimal sequence to generate it. So that's what this x-axis is. It's the construction step. So every time it will implement the right gate to generate it. And now we can compare between, just look at how fidelity and shadow overlap compares. In this setting, we see that, especially for bigger system, when we add in the right gate one at a time, shadow overlaps start to increase linearly towards 1. And at the very end, it becomes 1. However, fidelity has a much more like a barren plateau structure, like as we have seen before. Like even if we are putting in the right gate, it's still saying, oh, fidelity is 0 because the last few gates are wrong. Only until the very end it says we can do it. But note that this is the optimal sequence, which in general we don't know. So in practice, what we would see is what we would do is we will try to train the circuit, maybe by Monte Carlo or variational approach, and try to make it so that it becomes close. And we can use different loss function. We can say use fidelity, or we can use shadow overlap. So fidelity is bad in various regards. First, we don't know how to estimate it experimentally efficiently. And second, it actually has this barren plateau feature that allows us to be very hard to train. On the other hand, the best property of shadow overlap is that it can be estimated using single qubit measurement, which a lot of other quantity can have a hard time doing. And not only that, it also has this more like a Hamming distance flavor, which means when we try to train it, it behaves much more better. So here is an example where if we train it using shadow overlap versus training using fidelity, we see that when we train it using fidelity, it's just kind of randomly walking. And hence, if we evaluate the shadow overlap, it's very bad. And if we evaluate the fidelity, it's just 0. On the other hand, when we train it using shadow overlap, we see that as the optimization steps start to increase, the shadow overlap slowly, steadily increases, and then at the end, it becomes 1. On the other hand, fidelity is much more stricter. So when we see improvement from a shadow overlap perspective, we doesn't see anything in the fidelity case. Only until the very end it starts to shoot up and becomes 1. And that's because fidelity has these more like a barren plateau feature. On the other hand, shadow overlap is better than fidelity in 2 regards. First, one can estimate it efficiently by just performing single qubit measurement. And second, it doesn't have this barren plateau feature. So that concludes some of these applications. And now, just to conclude, in this work, we proved that almost all quantum states can be efficiently certified from few single qubit measurement, but this only holds for almost all. So right now, it's not entirely clear if one could prove or one can show that all quantum state can be certified efficiently using single qubit measurement. And to be honest, it's not even clear that the following question, does there exist some state that we can prove that it cannot be certified using single qubit measurement? And I think understanding that question is going to help us understand if the more ambitious goal of whether one can just certify all possible quantum state using single qubit measurements. That's it for my talk. Thank you so much for listening.
Yeah, thank you so much, Robert, for the very exciting talk. Maybe for time we have some time for quick questions. I think you already answered this question that so there was a question from the audience that most states can be certified using quadratic number of samples. Can you give an example of a state that this method doesn't work on? And I believe you just said that we just don't know if such a state exists, but we can't also prove that they don't exist. Is that right?
Yeah, in a way, that's what this question is about.
Yeah.
But actually, also add like the explicit there's actually a lot of variants, kind of similar to like classical shadow. One can have different variants of it. There's also a lot of variants of this procedure. So here I talk about like one version of it is we just pick one qubit, measure everything else in a fixed basis, and then measure that qubit in a random basis. One can also consider variants of it where we pick 2 random qubit or 3 and measure everything else in a fixed basis, but that 2 qubit in a random Pauli basis. I do have some examples where one needs to like have some example of state where if one just use like this 1 qubit version, then it would not be able to certify efficiently. But if one uses side variants like measuring 2 random qubit in a random XYZ basis, then suddenly it can be certified efficiently. So there are that example, but at the same time, like measuring 2 random qubit in an XYZ basis, that's still single qubit measurement, and hence the final question. So the specific one that I talked about, there are counterexample where one cannot certify efficiently, but one can look at a few variants of it, and suddenly it's not clear that there are states that
I
cannot be certified.
And the other question is, I think it's about calculating this, or maybe the sampling. So they're asking if, like, okay, classically performing the partial trace of the target state is not classically efficient in general. Is that a bottleneck?
Yeah, so here all the theorems that I talked about was mostly focusing on kind of information theoretic aspect, which means it just talked about how many measurements we need. But then we can also ask, what is the computational time? Like the measurement protocol is efficient, but then what is the computational time that requires us to do it? So the most computational, like potentially the most computation intensive part is really just this step. What is the ideal post-measurement state? Or more precisely, when I am given a bit string B0 and B1, can we estimate this probability amplitude efficiently? So this is also a kind of a, once you think about it, this is kind of a requirement of this procedure, which is also the same requirement as in like cross-entropy benchmark and various other protocols. So, so this is definitely a bottleneck of all of these existing protocol. There have to be some way of talking about what psi is. Like suppose I just have a psi being represented as a quantum circuit. And in general, it's not clear how one could estimate this. But there are also a lot of representation, like neural network representation, for example, is explicitly designed to be able to predict what this is, or tensor network representation, or if the state have certain structure that we already know of. So one have to, yeah, so one have to have a way to access this quantity, like the probability amplitude for some randomly sampled bit string. If we have that, then the whole procedure, the whole processing would be computationally efficient as well and can be deployed in practice. But for a very general or like very worst case situation where psi is just given to us as a quantum circuit, a very deep one, then it's not clear. Then it's not clear. So so definitely this is a limitation, but I would say it's not just a limitation of our protocol, but of a lot of or the wide range of all existing certification procedure.
So, and in like if you're given access to, like, this is a question from me, if you're given access to a perfect quantum computer, let's say
Yes.
you have an ideal quantum computer, you have your noisy quantum computer, but you can't swap this stuff, so you can't do a swap test for the certification.
Yeah.
Does it allow you to calculate this efficiently?
Ah, you mean like suppose does a perfect quantum computer allows us to calculate this?
Yeah.
It would help. I mean, there are situations where we cannot calculate it. I
Mhm.
mean, efficiently on classical computer, but we can calculate efficiently on quantum computer. There are situations like that that help, but I think in general, if I just have a very deep quantum circuit for preparing psi, I just give you that circuit, and now I ask you, what is this probability amplitude for some randomly sampled bit string? I'm not entirely sure what the complexity of it is, but I suspect in some worst case regime, it might be beyond BQP and hence not be computable
Right.
efficiently on quantum computer. Yes.
Okay. Yeah, thank you so much for this great talk.
You.
And yeah, we'll see the audience in the next seminar after the holidays. All right.
All
Thank
right.
you so much,
Bye.
everyone.